Okay, I use my okay, cool. So So we're continuing on with neutrinos in the inhomogeneous universe, and in particular, I want to tell you about neutrinos and structure formation, which concerns neutrino masses. And then in the second half, I'll tell you about relativistic neutrinos, free streaming, and the implications of that for non-standard interactions. So here we go. So this is basically the picture that we have at the moment about how structures form. So in the standard lambda CDM model, it also encompasses what we call the standard inflationary paradigm. And the idea here is that at the very early in the very early universe, you have essentially matter and stuff, a density field which is almost homogeneous. But then you have all these tiny fluctuations that are of order 10 to the minus 5. Okay, these are random fluctuations, and they come from well, quantum fluctuations on the scalar field that drove inflation. Okay. Now, the point is that these fluctuations are not just going to be static and sitting there doing nothing. They are, in fact, going to evolve. And they evolve because you have what is called gravitational instability. Okay. And so you can start off with something like this at the beginning, but then over time, so you have fluctuations that you can't even see, but then over time, the dense regions will become denser, the empty regions will become more empty. So in the end, you end up with a structure like this one, which is like maybe a galaxy cluster. Okay, so that's called gravitational collapse. So here's another schematic depicting what's happening. This is x, which is spatial direction. And then here I'm plotting what's called the density fluctuations. So you start up with primordial fluctuations in the matter density field, which is seeded by inflation. So it might look something like this if you just look at a cross-section of the space. And over time, they would end up looking something like this. Okay, so this here, which is initially dense, will become even denser. And by the time you have a very dense object, you have gravitational collapse, and you have formation of halos and galaxies. And then here's an empty region to begin with, and over time, it's losing stuff to the dense regions, so it becomes even denser. Okay, so that's a void over here. Now, so we have established that there is a cosmic neutrino background or relic neutrino background, and it has certain properties, right? It has a temperature of 1.95 Kelvin. Okay, we calculated that on Tuesday. We have also established the number density of this neutrino background per family. It's 100 and so per cubic centimeter of neutrinos and antineutrinos. And we also wrote down this expression for the non-relativistic energy density in these neutrinos today. Okay, and for masses that are maybe about 0.05 electron volt or so, we expect these neutrinos to be non-relativistic today. So then the question you can immediately ask is, can these neutrinos be the dark matter that are responsible, that are collapsing and forming halos? Well, the answer to that, I'm sure everyone knows. Well, no, you can't. Okay? The neutrinos cannot make up all of the dark matter. There's an obvious reason why that can't be so, and that is because if you demand that the neutrino energy density be equal to 0.25, which is what you need today to explain the dark matter, which is the energy content of the dark matter today, then the minimum mass that is required of the neutrinos must be 10 electron volt. Okay? And that is immediately at odds with what we know from laboratory experiments. In fact, it has been at odds with laboratory experiments for a long time. And these days, the latest limit from Katrin on the effective electron neutrino mass is 0.9 electron volt, which is 10 times smaller. Okay? So it's clear that this is not going to work. But there's also a deeper reason why neutrinos cannot make up all of the dark matter. And it has to do with the fact that the neutrinos, these relic neutrinos, are just way too fast. They have way too much kinetic energy. Okay? So they are technically non-relativistic today, but they still have a lot of kinetic energy. You can try to calculate what is the average speed of these relic neutrinos. So you just take, so this is V, average speed. You take the average momentum of these neutrinos divided through by the mass. The average momentum, you can estimate, this would be roughly equal to 3 times the temperature of this background, because we have a relativistic Fermi-Dirac distribution. So it's 3 times T of the neutrinos divided by the neutrino mass. And what you find immediately is that if you have a 1 electron volt neutrino, relic neutrino, then the present day speed of this thing, on average, is 150 kilometers per second, which is very fast. Now, this number by itself doesn't mean much. What you need to do is to compare it with the velocity dispersions that are typical of galaxies and galaxy clusters today. So for a galaxy cluster, the typical velocity dispersion is 1,000 thousands of kilometers per second. For galaxy, it's about a kilometer per second. Dwarf galaxies, much less than 100 kilometers per second. So if you compare the prediction for this Rayleigh neutrino with the typical velocity dispersions of various cosmological objects, what you find immediately is that you're going to have trouble forming dwarf galaxies, for example, with neutrinos. Yeah, they have too much kinetic energy. You can't pack these neutrinos into a tiny volume. Okay, now we can also, it's common to discuss how neutrinos cluster in terms of what we call the instantaneous free streaming length. And to understand what's happening here, you can again refer back to this schematic where I have this fluctuation that's in green, and it's the primordial density fluctuation. Now, to determine how this fluctuation will evolve, there are two time scales that I need to consider. One is called the instantaneous collapse time scale. And essentially, the idea here is that if you have a lump of stuff, you want to know on what time scale gravity acts to make it into a point. Okay? So that's the collapse time scale as given by this expression over here. So it depends on the gravitational constant, of course, and then also how dense this lump is. So that's why you have rho. So how long does it take for an overdense region to collapse to a point? That's your instantaneous collapse time scale. The second time scale relates to the speed of these neutrinos. Okay? And it's written like this. Lambda is the size of the region. So this length scale here is the typical size of this overdense region. You divide that through by how fast these neutrinos are moving. And essentially what this time scale tells you is how fast is a neutrino able to escape from here to out of the region. Okay? So then the two behaviors, the two limiting behaviors are clear. First, you could have the growth behavior. Okay? So here what happens is that the collapse happens faster than the escape. Okay? In other words, the collapse time scale is short relative to the escape time scale. So you collapse things very quickly, the neutrinos don't manage to escape, then what you end up with is growth. Okay? The other limit is erasure, and this happens if it takes forever to collapse that point and the neutrinos fly away during that time. Okay, so if you have delta T collapse being much larger than delta T escape, then the perturbation will be erased. Okay? Now, delta T collapse will be written down. Lambda is just the length scale of the perturbation. V we also have from the previous slide. So immediately what we can do is to define a thing called the instantaneous free streaming length scale, which I call lambda Fs. And that is just defined by demanding that the collapse time scale be equal to the erasure, collapse time scale be equal to the escape time scale. That's the demarcation between the two limits. And when I do that, what I would find is something like this. And you can see that it's obviously dependent on the neutrino mass, this length scale. And it also depends on how much stuff you have in the universe that can collapse. And it's a function of redshift, which must be the case because your neutrinos are initially very fast, and then they slow down and slow down and slow down. And so it makes the collapse easier and easier at later times. So what this means here is that unless your density fluctuations are regenerated by some other means, if you have a universe that is made out of neutrinos entirely, so just neutrino dark matter and nothing else, then on any length scales that is smaller than this instantaneous free streaming length scale, you would not be able to form structures on those small scales at that particular time. Okay, that's the meaning of the instantaneous free streaming length. Now, so this is obviously redshift dependent, but I can also ask myself, what is the maximum instantaneous free streaming length throughout the history of the universe? And I can estimate that by simply saying that, well, okay, the maximum free streaming length would be essentially the instantaneous free streaming length at the time when the neutrinos become non-relativistic and can start to cluster like matter. Okay, so what I can do is to substitute in, whenever I see 1 plus z, I substitute in 1 plus z nr, nr for the relativistic to non-relativistic transition. That's roughly equal to the mass divided by the neutrino temperature. Once I stick this in, I find an expression like that. Okay, you don't have to, I mean, it's just there. Don't worry about copying it down or anything like that. And this maximum instantaneous free streaming length scale would correspond to the maximum size of objects that could not have been formed in a neutrino dark matter only universe. Okay, so then if I am to now put 10 volt evaluate this number, I will find about 45 immediately is have formed galaxies, because galaxies are only like 10 kiloparsec, 50 kiloparsec across. Galaxy clusters are about 1 megaparsec across. And if my neutrinos are free streaming so far, 45 megaparsec, you will not be able to form any of these objects in this kind of universe. And that's the reason why it is that we cannot have standard model neutrinos as the dark matter. Okay, so here's a nice simulation that was done by Charles Haug-Böhler. I'm not actually sure where he is now, but so what's happening here is that you have two universes. The one on the left has cold dark matter, and the one on the right is the case of kind of mixed dark matter. There's a little bit of cold stuff at 10%, but most of it, 15%, is neutrino dark matter, corresponding to a neutrino mass sum of about 7 electron volt. And what you see, and I'll play it again, is that initially these two boxes look practically the same, okay? But as you evolve these two boxes forward in time, what you see is that the box on the left has a lot of fine structures, the little tiny dots all over the place, okay? Whereas this one over here, if you squint your eyes, you can see that there's some filaments here which are also present in the box on the left-hand side. But this box over here on the right-hand side does not have all the fine structures, all the little dots. Okay, so these little dots here are the small-scale structures. The small structures, and it's because of the fact. And in the the box on the right, it's because there's free streaming of the neutrinos, and the free streaming of the neutrinos are preventing the small structures from forming. Okay, that's the same thing. Now, then you can ask, okay, if the neutrinos are totally useless, as a dark matter candidate anyway, why are we even talking about this whole thing? Well, we're talking about it because we know neutrinos are massive. Okay, we have evidence from neutrino oscillations that provide a lower limit that at least one neutrino mass eigenstate must have a mass that is larger than 0.5 electron volt. And on the other hand, we have these tritium beta decay experiments in the lab, and they provide an upper limit on the effective electron neutrino mass of about 0.9. So these basically are predictions, if you like, okay? And if you stick these two numbers here into this expression for the reduced energy density in neutrinos, what you'll find immediately is that I should expect to see 0.1% to up to 6% of the energy density of the universe today to be made out of neutrinos. That's a prediction. So this is something that we can immediately test for. Okay, so even though the neutrinos at these kind of reduced energy densities cannot be the dark matter, they are still subdominant. They can still be a subdominant kind of dark matter. And because the free streaming behavior of these neutrinos is such that they are totally different from what you would expect from cold dark matter, we can still try to look for imprints of the free streaming, and from there to see if we can turn the argument around and set a bound on the neutrino mass. Okay, so that's the reason we're doing it. Okay, so just to make sure that everyone is on the same page, we're not trying to explain the dark matter with neutrinos here. That can't be done. Okay, not with standard model neutrinos anyway. We're only looking at what might happen if you have a subdominant contribution somewhere in this pi. Okay. Now, okay, so we're looking at subdominant contribution. And so most of the dark matter is actually in cold dark matter. So you have this mixed dark matter universe where the cold dark matter are kind of providing potential wells for the subdominant neutrinos to fall in. Okay, and that would actually lead to a very interesting behavior, and that's what I call potential decay of the dark matter, and I'll show you what that means in the next slide. Okay, so in this schematic here, what we have are two potential wells, and one is very large, okay, large in spatial extent, and the other one is smaller than the instantaneous free streaming scale. And we're in a universe that has both cold dark matter and neutrino dark matter. Now, you will have potential wells. These are essentially provided by the cold dark matter because they are clustering. And you can ask, if I have a cold dark matter that encounters a potential well, what would happen to that cold dark matter? So that's the blue particle over here. Now, cold dark matter by definition is something that doesn't have much kinetic energy. So when they encounter a potential well, they will just fall in. So that's what happens. And similarly, if you have a cold dark matter particle that is already sitting at the bottom of the potential well, it will not have sufficient kinetic energy to fly out again. So the cold dark matter is just going to be falling into the potential well and contributing to the potential well. The neutrino dark matter, on the other hand, well, it's free streaming. Okay? So when it sees the potential well, whether it falls into the potential well or not depends on how large the potential well is. Okay? It depends on the instantaneous free streaming scale relative to the scale of the potential that you're looking at. So in this case, in the large potential well, the neutrino that comes in sees the potential well, it would eventually be captured because I have large potential. On this side, on the right-hand side, on the other hand, this is a tiny potential well that is very narrow in extent. And the neutrinos, when it comes along, it doesn't even see it. It will just fly by and say, oh, okay, missed it. Okay? And this one here will fly away and won't fall in. And similarly, if you have neutrinos that are originally sitting at the bottom of the potential well, in the case of the left-hand side, this one won't really be able to fly out. Okay? This one, on the other hand, will just escape because it's easy for us to escape. Okay, so that's a hand-waving explanation. We can do this kind of simulations to actually see that this is happening. So this is actually one of our simulation, and what we have here is a box that is 256 megaparsec across. This is the cold dark matter component, which you see where you see a lot of tiny fine structures. And this is the neutrino component, the corresponding neutrino component. What we have put in is a pretty large neutrino mass at 0.5 electron volt, but you can see that so you have a blob here which corresponds to that blob, but for the neutrino component, it's all kind of smeared out because of the free streaming behavior. And in fact, you can even look at the neutrino behavior momentum by momentum. So this is a fairly low momentum, which looks more like the cold dark matter. But the faster ones are getting hazier and hazier because they're moving so fast and they're escaping from potential wells. Okay. Now, what's more is that, so going back to this schematic, so as I said, the potential well on the left-hand side is able to capture both neutrinos and cold dark matter, right? Whereas the potential well on the right-hand side can only capture cold dark matter. So if you wait a little bit of time and ask what's going to happen to these two potential wells as a result of this differing behaviors of what they're able to capture, what you'll find is that the potential well on the left-hand side will stay the same depth. At least that is so during, I should say matter domination. Sorry, I should update my slide. I should say matter domination. Okay. Whereas the well here on the right-hand side, because it's only able to capture cold dark matter, this potential well will decay away. Okay? Now, this sounds kind of odd, but when I say potential, I'm really talking about these perturbations in the metric in the conformal Newtonian gauge. Okay? The psi parameter and the phi parameter will remain constant during matter domination for this potential well on the left, but for this potential well, these two parameters here, metric fluctuations, will decay away. And that's basically the whole idea of cosmological neutrino mass measurement. All we're trying to do is to observe this kind of potential decay that is scale dependent. Okay? Yeah. So what I mean essentially is that if you solve the equations of motion for psi and phi, which are the metric perturbations, if you only have cold dark matter, then there's a very nice fine balance between expansion during matter domination and the clustering. And so you will have these two terms here, phi and psi, being constant. Okay? But once you upset the balance and you have an expansion rate that is like matter domination, but then the clustering applies only to a fraction of the dark matter. It applies only to the cold dark matter, but not to the neutrino dark matter. Then you have an imbalance, and that imbalance will cause psi and phi to decrease with time. Yeah, and so you have on the large scales no decreasing of the potential. On the small scales, you have decreasing of the potential. So you have this scale dependence. Okay, so that's the potential decay when I said that's what I meant. Sorry, I didn't hear you. Couldn't you? Yeah, so in this case, what would happen is that you will have on the large scales, you have the structures looking more or less the same as if you were in a cold dark matter only universe. But once you go to the small scales, you find fewer structures because on the whole, the potentials have become less. Yeah, it's the same. Majorana, Dirac, it doesn't matter. There's no difference. This is just gravity, and gravity doesn't distinguish between Majorana versus Dirac. No, 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 not at all. I mean, quantum numbers are not that the gravity here, classical gravity, doesn't care about your quantum numbers. So I could apply the same picture to describe any kind of non-interacting relic fast particle species, axions, if you like. Yeah, it's not particular to neutrinos. It's just fast particles versus slow particles. Yeah. Okay. So so what I have here is another schematic that shows what we call the perturbation wave number. Okay, and the perturbation wave number is defined as k, and it's basically defined as 2 pi divided by lambda. Lambda is the size of your potential wells. Okay, so in other words, when I'm looking at small wave numbers, I'm looking at things on large scales, and large values k correspond to things that happen on small scales. So if I have two universes which have, and this is a spectrum, okay, perturbation spectrum, which corresponds essentially to the depths of the potential wells, okay, on different scales. Okay. Now I could have two universes where one is cold dark matter only, that's the blue. I could also have a universe where you have a mixture of cold dark matter and neutrino dark matter. That would be the dashed red line. That's what you started with initially. Yeah. Yeah. Matter domination. Yeah, I had a mistake in my slide, which I have to fix. So okay, structure formation only happens during matter domination. Okay, if you have radiation domination and everything is relativistic, everything kind of gets pushed out. Okay, so we're focusing really on matter domination. Now, if you have matter domination and a cold dark matter, okay, cold dark matter has no has not much kinetic energy, has very little kinetic energy. So what happens is that um, when you have potential wells, the cold dark matter will just fall in and make the potential wells stay the same depth. Okay. Now this sounds kind of weird, but when we talk about potential wells in cosmology, what we really mean are these metric perturbations defined in a very particular way. Okay. So if you have a cold dark matter universe, then these metric perturbations remain constant during matter domination. Okay. You would also have these these metric perturbations remaining constant if you are looking at a mixed neutrino plus cold dark matter universe, but on very large scales. Because on very large scales, the neutrinos will fall into potential wells just like cold dark matter can fall into potential wells. So in other words, on large scales, the neutrinos are essentially behaving like cold dark matter. But if you go to the small scales, then you start distinguishing between these two types of dark matter. The cold dark matter will still fall into the small potential wells because they have no kinetic energy, but you would have trouble capturing the neutrinos because they fly fast and they don't see the small potential wells. But the fact that they're free streaming means that it changes the way the perturbations grow. Yeah, yeah. But anyway, the net effect is that if you go back to refer to these potentials in inverted commas, or metric perturbations, for on the right-hand side, these things decay away. They decrease. Okay, so constant phi and psi, decreasing phi and psi. That's the bottom line. Right? Okay. So going back to this, so you could have a universe that start off with essentially the same spectrum of perturbations in these two universes. Okay? But if you wait some time later, what you will always find is this step-like feature developing in the mixed cold and neutrino dark matter universe because of this free streaming behavior. So you can start out the same, but the neutrinos will just start free streaming, will start with free stream on small scales, so you will always get this kind of potential decay, and the spectrum of perturbations in the end will be smaller here on the small scales or large wave numbers. Okay? And roughly where the transition occurs corresponds to the instantaneous wave, free streaming wave number, which corresponds to basically the instantaneous free streaming wave number at the time the neutrinos become non-relativistic. Okay, something like that. Okay, so what we're looking for is a step-like feature like this. So that's my schematic. This is a real calculation from linear perturbation theory. And you can see here that the green line corresponds to just lambda CDM, where I have massless neutrinos, but no massive neutrinos. And the blue line here corresponds to the case where I have replaced some of the cold dark matter with neutrino dark matter, okay, with the mass totaling. So in this particular example here, I have one massive neutrino of 1.2 electron volt. I picked this pretty large mass just to exaggerate the signature, okay? And you can see here that these two lines are overlapping on large scales, so at small wave numbers. But once you go to smaller and smaller scales, they deviate. And you see a suppression here in the case where the neutrino mass is large and finite and large. Suppression goes roughly like F nu, which is defined as the reduced energy density in neutrinos divided by the reduced energy density in the total matter content. Okay, and omega nu here we've seen before, it's essentially proportional to the sum of the neutrino masses. And that's why it is that cosmological neutrino mass bounds are always presented as a bound on the neutrino mass sum, because the leading order signature is this suppression, which is essentially proportional to the mass sum. Okay? Now, if I was to change the mass spectrum, okay, let's say I have inverted versus normal hierarchy versus 3D general neutrino masses, you will see some minor differences. Yeah, you'll see maybe some small variations in the small scale suppression. You'll also see some variations here in these intermediate scales, because the free streaming scales are different. Every time you put in a new neutrino mass, you have a different free streaming scale. So if you have different neutrino mass spectra, the prediction will be slightly different. But the zeroth leading order prediction is this suppression, which goes like the neutrino mass sum. All right. Okay, another picture of the large scale matter power spectrum. And here what I have plotted is basically these various scenarios with different neutrino mass sums normalized by the case with zero neutrino mass. Okay, and you see here immediately that the larger the mass sum, the larger the suppression that you should expect. Now, who can measure it? Well, a lot of people can measure it. A lot of different surveys are sensitive to this matter power spectrum. So on large scales, most of the measurements that we have on this matter power spectrum is coming from the CMB primary anisotropy in particular. And you also have CMB lensing potential, which is basically the gravitational lensing of the CMB photons from a large scattering surface by the intervening foreground large scale structure. That's primarily sensitive to large scale structure that is at about, say, redshift of 3 to 4, maybe a bit lower. The clustering surveys, these are big galaxy catalogs where you look at the angular positions of your galaxies and their redshift. That's also a probe of the power spectrum. Okay, BAO is a baryon acoustic oscillations peak that is a feature. Sorry. Cosmic shear is sensitive to smaller scales, and that's basically a term to describe the gravitational lensing of distant galaxies. Okay, so you have a galaxy that might be elliptical like that, but because of lensing, you will see slightly more stretching, maybe some kind of shearing of this image. That's cosmic shear. So abundant is basically another word for looking at galaxy clusters of different masses, and then you bin them by their masses and their redshift. So that's also a measure of how things are clustering. And Lyman alpha for us, that's these are the hydrogen clouds that are sitting in front of quasars. And so you look at the way the quasar light is absorbed by the hydrogen cloud that is sitting in front of it. And you get more absorption if you have denser regions of the hydrogen cloud, less absorption if it's less dense. And you can look at the amount of absorption to determine how the fluctuations in the hydrogen clouds are distributed. Okay, so these are all measurements of the the power spectrum that we have at the moment available. Okay. Now, so you have measurements spanning all scales, and roughly speaking, what they do is that you have these large scale measurements from the CMB, which are providing an anchor for a lot of the cosmological parameters, like the matter density, omega b, which is the baryon density. It anchors also a couple of primordial parameters. So NS is the spectral index from inflation. AS is the primordial fluctuation amplitude. Tau is an astrophysical parameter that tells us about the optical depth to reionization. And H is the reduced Hubble parameter. So all of that comes from essentially the CMB primary anisotropies, which serve to anchor this part of the power spectrum. And then, of course, you can also combine with these other small-scale measurements. They are essentially giving us more information about the geometry of the universe, physical matter density as well. And these very small-scale measurements are primarily responsible for telling us about the small-scale fluctuation amplitude, which usually goes under the name of sigma 8. Yep. Now, that's all I will say about measurements, because I don't really do observations at all, so I can't really say anything more insightful than that. But that's one thing I do want to point out, and that is this picture here has been, these two curves here have been computed using linear perturbation theory. Okay, so I sort of briefly mentioned that yesterday. You take a GR theory, you take a theory that involves perturbations in the stuff, you linearize this, and then solve the resulting linear order equation of motion. This is a pretty good idea on large scales, but now when we look at the picture over here, you have the large scales on this side, and you also have these small scales on the right-hand side. So at some point, we would expect this perturbation theory to fail. And indeed, it does fail, and it fails roughly here. Okay? So this thick red line here corresponds to the point where I can expect linear perturbation theory to be accurate to about percent level at the present time. Okay, so it's roughly here. And if I go back to an earlier time to redshift of 1, then the failure point is here. Redshift of 3, the failure point is over there. So everything on the right-hand side, you can compute using linear perturbation theory very well. Everything on the right-hand side, these curves here are actually wrong. Okay, I'm showing them anyway because they're easy to generate, but they are actually not correct. Okay, the actual curves that I should expect to see today are including nonlinear dynamics, are different. Okay, so um, now, but that's even that is not the whole story because there are nonlinearities and nonlinearities, and they are not all equal. And all these probes that I have shown in the previous slide are subject to nonlinearity just by looking at where they are positioned relative to this failure line, okay? Except the CMB. The CMB is definitely linear, but everything else is kind of nonlinear. But even then, the nonlinearities are different, affecting each probe is different. So CMB, as said, is it's totally linear. But if I look at the BAO, we can already expect some mild form of nonlinearities coming from, for example, collisionless nonlinear dark matter evolution. Okay, if you're using galaxies to as a proxy to as a tracer of the perturbations, then you will also have some mild amount of nonlinearities coming from the fact that your tracer may be slightly biased relative to the underlying dark matter field. Okay. Cosmic shear, again, is quite nonlinear because you're subject to nonlinear dark matter dynamics and so on. Okay. Now, these three columns here, I didn't explain, and I should explain it. I classify them into three types of nonlinearities because some of them are actually more tractable than others. So in particular, this nonlinear dark matter dynamics, collisionless dynamics, this is a kind of nonlinearity that is calculable from first principles, in the sense that I can write down a Lagrangian, derive my equations of motion, and all I have to do is to stick these things into a computer and solve them. Okay, so that's a kind of nonlinearity that is probably not too bad because we have a theory, a fundamental theory to describe them. We are limited only by numerical resolution. Okay? These two types of nonlinearities, on the other hand, depend on empirical modeling. Okay, so for example, these probes here that are subject to baryonic astrophysics require inputs about star formation, for example, or supernova feedback. Okay, and these are the kind of things that I cannot predict at all by writing a Lagrangian. The only thing I can do is to take observations and then say, okay, star formations seem to be happening in this particular way, and therefore I write down a power law to describe it. Okay, so that requires, to predict these probes here, you need to put in baryonic astrophysics of this sort that cannot be described by a Lagrangian. Okay? Similarly, with tracers and proxies, if I make the statement that galaxy clustering is approximately tracing the clustering of dark matter, which sounds like a good idea, but again, this is not something that I can really write down a Lagrangian to describe. Okay, so I can either look at observations to establish what this relation might be, or I can try to run some simulations with some semi-analytical approximation in there, but again, it's not something that's fundamentally predicted. Okay, so that's the three types of nonlinearities that I want to highlight, and different probes suffer from different types of nonlinearities. Now, just a little bit more on the fairly easily calculable kind of nonlinearities and how they affect the neutrino signature. So here, this is a picture from one of our own papers, but a lot of people have done this kind of thing. And what you see here in the purple line is the prediction of the suppression due to neutrino masses calculated from linear perturbation theory. Okay, that's a purple line. And if you try to go to higher order in your perturbation theory, then that's the green line that you see over here. So what you see immediately is that in general, including nonlinear dynamics, you get a little bit more suppression, at least over here. But as you can see also in this picture, perturbation theory, even if you go to higher order, is not necessarily a good idea. And in fact, if you do a non-perturbative calculation by running an n-body simulation, what you find is that this suppression actually goes back up a little bit in the end. Okay, so that's the non-perturbative result. That's still a perturbative result, but including high order corrections. But nonetheless, the point to take home is that nonlinear dynamics has to be included when I'm predicting the neutrino mass signature on these small scales, these wave numbers that are at about say 1 inverse megaparsec. Now, Um, how do you do n-body simulations? Well, just a quick word on how you do that. Uh, N-body simulations is a fairly standard method for computing nonlinear cold dark matter dynamics, and the idea is that you put in, you start a simulation box, and you apply periodic boundary conditions. It's periodic boundary conditions which makes sense for cosmology. We have the cosmological principle, which states that things should look more or less alike anywhere in the universe. Okay, so this is reflected in the periodic boundary conditions that we apply to the box. And once you've defined your box, what you can do is to imagine that you have a cold dark matter fluid in your box, and then you discretize this fluid. Okay, so you cut them up into chunks and represent each chunk with a particle, with a point-like particle. Okay, now for typical cosmological simulation, you would need about 10 million to maybe 10 billion particles in your box. And then what you do after that is to kick them a little bit, displace a little bit, these particles off their grid points a little bit, and then solve these fairly standard looking equations of motion to see how these particles move under each other's gravity. So that's an n-body simulation. Okay, so you solve the equations of motion, and the Poisson equation here gives you the potential that these particles move under. Okay? Now, okay, that's a very simple schematic. There are details of how to actually make this work efficiently as well as accurately. But that's the basic picture of how you simulate cold dark matter. Now, what about neutrinos? How would I simulate neutrinos? Well, we can, in principle, do the same thing as well if I was to include neutrinos in my simulation to predict these nonlinear signatures. But there are several reasons why this is very difficult. And the reason is free streaming. Okay? The one reason is free streaming. The main reason is free streaming. Okay? So as we have already discussed, you have this neutrino background and it's moving around. Okay, the neutrinos are moving around at very fast speed. They're also not just moving in one direction, they're dispersive. So you have neutrinos moving this way, this way, and that is true at every point in the universe. You always have a dispersive kind of substance at every point in the universe. So what this means for this simulation is that if I was to try to simulate these neutrinos in sort of the same way as I would simulate cold dark matter, what I have to do is to use several neutrinos per cold dark matter particle to simulate this dispersive effect. Okay? So that's already kind of difficult because I said that you need 10 million to 10 billion particles to even simulate a cold dark matter. Now I have to add at least another 5 times 10 billion or whatever to represent the neutrinos. That's going to be a strain on your computing resources. Okay? That's one reason. The second reason is that these neutrinos initially are also moving very fast. So what it means is that you've got to be very careful with tracking where these neutrinos are going. Your time stepping has to be very, very accurate. Otherwise, the neutrinos fly off and they end up somewhere, and that's probably inaccurate where you have where they land if you don't use a good time stepping to see where they end up. Okay. So in practice, this sort of simulation is nasty. They take a long time, and they are also very much plagued by short noise. Okay, because you just have so many random things there, and you don't have enough samples to sample them properly. So it's not like they can't be done, and some people do this kind of simulations. But let me also highlight that there are actually a lot of cleverer ways to do this, and that's a fairly active area of research to how to decide to figure out how to simulate neutrinos in an accurate way. There's a partial review of this problem in this review that came out in 2021. So that's all I want to say about simulations. If you are interested, you can read this review. Okay, just a summary of the current bounds on neutrino masses. Now, okay, there have been a lot of analyses in the literature of what we expect the neutrino mass bound to be. So I'm not going to summarize them all. I'll just say that the current constraints on the neutrino mass sum is roughly in the ballpark of 0.1 to 0.3 electron volt, depending on exactly who's doing the analysis, which data set they include, what background model they assume. But I do want to highlight the following, and that is the model dependence. Okay, so this table here is it's taken out of this paper from 2019, and what I have here are three columns. Okay, so this here describes the model, the background model that I'm using to do the analysis, and this here is the baseline lambda CDM plus neutrino mass fit, which is the one that you will find reported in most papers coming out of the like Planck or the big collaborations. And there's three columns over here, and this one here corresponds to three degenerate neutrino masses going into this neutrino mass sum. The second column here assumes a normal hierarchy, okay, distributed in here. And the last column corresponds to the bound that I would get if I use the inverted hierarchy to do the fit. And then over here, I have different models. So this model here would also include primordial tensors into my fit, or I can add a dynamical dark energy into my fit that would correspond to these three cases, as well as spatial curvature. And what you can see here, if you just kind of eyeball the table, what you find immediately is that there's generally a factor of 3 variations between the lowest number that you get compared with the largest number that you would get from doing these fits. Okay? Okay, so here, this is dynamical dark energy, but you limit it to non-phantom behavior. The mass bound, if you assume 3 degenerate neutrino masses, is 0.96. But once I allow for in an inverted hierarchy and dynamical dark energy, this bound relaxes to 0.276. Yeah. Yeah. No, this is entirely Planck plus BAO, if I remember correctly, what these people, yeah, Planck plus BAO. You could make it more aggressive, but so for example, usually if you have dynamical dark energy in your fit, you can constrain this more if you put in supernova. Yeah, but we can argue about whether you believe the supernova data or not. Yeah, this one. Yeah, 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 yeah. Well, if you this is the Planck fit, yeah, Planck plus BAO, yeah. So the thing is that I mentioned it yesterday. So the reason why you see this number from the Planck collaboration is that it's when you do these fits, every time you introduce a new neutrino mass, you basically have to solve 20 times more equations of motion. So if you have inverted hierarchy with 3 separate masses, it takes forever to do the fit. That's why they don't do it. They're lazy, essentially. Yeah. Yeah. No, no, no. These guys, this who was a student at that time, he actually ran the MCMC with 3 different masses. Yeah, it's not a prior, not at all. It's actually 3 different masses. Took him forever, weeks to do the MCMC, but he did it, and I'm glad he did it, so I can show it to you. Yeah, yeah, yeah. No, that's the prior is free. So they they just say 0, mass is 0 to whatever, 1 electron volt. Yeah, and that's yeah, these numbers. So it really is a difference in how they did the analysis in terms of the modeling. Yeah, they explicitly accounted for the fact that you could have 3 different masses. Yeah, right. So the bottom line of this showing you this table is that there are variations in the mass bound depending on exactly how you do it. Okay. And also that when you read some of the papers out there are sometimes approximations that you should be aware of. Okay. Okay. Now, so as said, you already see this relaxation in the like there's this least constraining bound is the inverted hierarchy and then dynamical dark energy. Okay. Now, that's typically factor of 3 is typically what you would get if you play this sort of game by making your cosmology more complicated. But if you are adventurous, you can actually these bounds even more if you play around with pseudo physics. So some of the things people have looked at are things like neutrino decay, spectral distortion, late-time neutrino mass generation. And if you play these physics, neutrino physics games, that usually buys you a bit more room for play. Okay, and I'll show you in a bit what I mean by more room. But they are kind of slightly out there kind of physics, so you have to decide if you are willing to accept them. Now, so this case here is non-relativistic neutrino decay, and what these guys have done is to assume that neutrinos decay with a lifetime of about 0.1 years. And what they found is that the best fit will correspond to this point, I think. And in that case, you can actually relax the bound to 0.42. So what they did here is degenerate neutrino masses, BAO and Planck and supernova. And this is like roughly a factor of 3 relaxation relative to the Planck benchmark. Okay. Another case here is from these guys over here. And what they did, there's Gabriella's over there. It's one of yours. And what they did here is to assume that, yes, sorry. Yeah. This is the basic, most basic lambda CDM. Yeah. They didn't put that in. They could have, I guess. They didn't. Yeah, they didn't. This is, as I understand, this is just lambda CDM plus neutrino mass. But then they allow the neutrinos to decay as well. Yeah. Yeah. This is the next one is an older paper from 2019. They fitted the Planck 2015 data, and this particular scenario here is a potential deviation of the neutrinos distribution from a Fermi-Dirac distribution. So the standard prediction is that the neutrinos should have a relativistic Fermi-Dirac distribution, but it's possible that something, a decay or whatever, may kick this distribution out of shape. Okay, and in particular, if the distortion is such that you shift the average momentum of the distribution to something higher, then it turns out that that would also lead to a relaxation in the neutrino mass bound. Okay, and in this case, we're talking about maybe a factor of 2 or so, but that was relative to Planck 2015 data. Okay, if you are adventurous and totally depart from Fermi-Dirac distribution and say, oh, let's say I have a Gaussian momentum distribution, utterly crazy. I don't know what process will give you a Gaussian momentum distribution. You could even relax the bound to 3 electron volt. And that was basically pushed by Miguel Escudero. He likes to play these games. Okay, I'm not saying you should believe it, but this highlights the fact that there are assumptions going into these bounds. Last but not least, this is a case, a proposal by Dvali and Lena Funke, where they proposed a scenario where the neutrino mass does not become finite until a much later time. Okay, don't ask me the details of that scenario. I don't really know. I think Gabriella knows better how that works. But the bottom line phenomenologically is that you have 0 neutrino mass until up to a very late time, and then suddenly you have a phase transition and the neutrinos become massive. And so what these people did in a phenomenological analysis is to ask, if I have this scenario where the neutrinos don't have a mass until much later, how large, what is the bound, okay, that I could have if, say, for example, if the neutrinos only pick up masses after a redshift of 1, okay? Then what they find is that if that was the case, that neutrinos are massless essentially for most of the history of the universe and only become massive after a redshift of 1, then the bound relaxes to 1.46 electron volt. Okay, so I don't know if this is a particularly theoretically well-motivated scenario, but phenomenologically, this is what the data is telling us, that if your neutrinos are essentially massless throughout time and don't become massive until later, such a large mass is actually okay. Okay, so take-home message so far is that massive neutrinos leave an imprint on the large-scale structure, and we can use that fact to constrain neutrino masses from cosmology. Okay, right. That's only the first part. I still have more to say. I don't know if you want to hear it. That's only. I don't know. I can be kind of fast. It might take a while. I'm giving that talk next week anyway. I just realized when I look at my slides today that okay, I will just say some essential points because I think it's kind of yeah, it's already 12. I started late though. Don't forget. Yeah, yeah. I don't know. I will say the main points. Yeah. So what I've talked about so far with neutrino masses is that we've been looking at free streaming of non-relativistic particles and how that affects clustering. Okay. But I can also think about free streaming of relativistic neutrinos. Okay. And this is not something crazy because in any case, the neutrinos are relativistic to begin with. So they decouple at an early time. Okay, so you have interactions at early time up to temperature 1 MeV, and then after that they free streaming to infinity. Okay, so they free stream and they're relativistic. Now, fundamentally, there is no different. There's no difference between this kind of relativistic free streaming and the non-relativistic free streaming that we talked about earlier. But there's one distinguishing feature between non-relativistic free streaming versus relativistic free streaming in the phenomenology. And that is, if you have a relativistic particle and it is free streaming, then it can develop significant pressure as well as what we call anisotropic stress. Okay? Non-relativistic particles, you wouldn't have pressure because it's non-relativistic, not much kinetic energy, so the pressure would be less than the rest mass energy. Similar with the anisotropic stress. But in the relativistic case, these things can develop and they can be very large. Now, so what it means is that if I'm to write down a stress energy tensor like that, that would be my unperturbed part. I will have energy density, not the pressure terms. And there's also the perturbed part of the stress energy tensor. And essentially, I'm referring to large contributions to delta P, and then anisotropic stress here, which are in the off diagonal. Okay, so that's what you get if you have relativistic particles that are free streaming. Now, just to understand how the free streaming comes about, the free streaming comes about because you have a background that is inhomogeneous. Okay, so you have particles that are moving in all directions, but they're not moving in a smooth background. They are moving in a background that has inhomogeneities. So if I represent the inhomogeneities by this yellow thing here that indicate a series of sinusoidal gravitational potentials, you will have a peak, a trough, a peak, and a trough, and a peak, and a trough. Okay? Now, if I think about one neutrino fluid element that is sitting right here at the top of the potential well, then for those neutrinos that are moving up and down, what they see is different from those neutrinos that are moving in the horizontal direction. Okay? So those neutrinos that are moving horizontally at the peak of a potential, as far as they're concerned, space is flat. Okay? But those ones that are moving up and down here, they will experience the potential. So if they're at the top of the potential and they start moving, then the first thing that will happen is that they will fall into a potential well and pick up some more kinetic energy as a result. And they will climb up, lose potential energy, fall down, so on and so forth. Okay? And so what this means is that those neutrinos over here would generally be a little bit more, have a bit more kinetic energy compared with these neutrinos that are moving in the horizontal direction. And that's what we mean by an anisotropic stress. Okay, in other words, and our term for it is momentum anisotropy. Okay? Now, this is interesting. This anisotropic stress is interesting because now we go back to this metric perturbation that we saw earlier in the conformal Newtonian gauge, and I have these perturbations psi and phi. Okay, these we've been calling gravitational potential, but in GR, if you take the difference between phi and psi, this difference is actually proportional to the anisotropic stress. Okay, and in lambda CDM, this anisotropic stress is mainly coming from ultra-relativistic neutrinos at early times and photons. And the fact that you have phi minus psi will influence the way the CMB temperature power spectrum evolves. So if I was to change it by, for example, taking away some of this anisotropic stress, I'm going to end up seeing something in the CMB. Okay, and in fact, this is something that people have thought about even back in 2005. So this is a picture from a paper from Steen, Hannestedt. And you can see here, the solid line is the case if you have just standard model neutrinos that are free streaming. And in the case here, in the dashed line, what he did is to set the anisotropic stress in neutrinos to exactly 0. And what you find is a totally different signature. You see a bit of an enhancement in the power in the CMB-TT power spectrum at multiples larger than 200. There's some mild degeneracy of this effect with other parameters, but even back then in 2005, when we only had WMAP first year data, it was already possible to exclude this kind of zero anisotropic stress at the 2 sigma level. So that was one paper in 2005 that pointed that out. There was a second paper as well by Roberto Chotta and Alessandro Melchiori, essentially, with a slightly different modeling, but they were essentially pointing out the same thing, that if you remove the anisotropic stress, you see something. So what can we do with this? We can do a lot with this, actually, and that is because to see the anisotropic stress in the first place, you need the neutrinos to be free streaming. So you can ask the question, what if my neutrinos are not free streaming? Okay, what if they're interacting instead? So why should interactions change the picture? Well, interaction will change the picture because if you think about the simplest case of a scattering, okay, so I have two neutrinos that are coming together horizontally and they scatter. What the scattering does essentially is that it transfers the momentum from one direction to another direction. Okay? And if this scattering is happening very efficiently, you could start off with something that's anisotropic, but eventually the scattering would make it isotropic again. Okay? So we can use the fact that the CMB data prefers there to be anisotropic stress than no anisotropic stress to constrain these scenarios where you have interactions. Now, they will have to be non-standard interactions, must be, because the weak interaction won't give you this kind of behavior at CMB times. But you could definitely imagine cases where you have non-standard self-interaction of the neutrinos, for example, and try to place a constraint on that. Now, I don't really have time to say any more about that, but So I'm just going to go to the last slide and give you my conclusions. You can constrain non-standard interactions with a CMB by making use of the fact that the CMB data actually prefers there to be anisotropic stress in the neutrinos. And if you had interactions, you wipe away the anisotropic stress. That's a relatively new thing. Well, it's not that new. Some groups work on it, but I guess it's not so widely known, but it's fun. So anyway, that's all I have to say, and I'm going over time. And thanks for your attention. Yeah.
Thank you. I was just wondering on the plot where you showed CMB with the anisotropic stress. I was trying to understand, like, intuitively why it specifically makes, like, I think it was like maybe like the third peak or something, or
which one are you looking at? Like this one?
yes. So it makes so it just makes the power increase on like all scales. Is that right?
So it's a causal thing. So it will only happen at L of larger than about 200. Okay, maybe this is not a very clear plot. So we also have another one over here. So this is a case of decay, but so okay here. So this here is basically the lambda CDM case versus the case where you wipe away the anisotropic stress. So you see an enhancement around 100 or so, and then some here, and then they drop away. Yeah. So practically all scales as far as the CMB is concerned. Yeah. But
Thanks.
maybe, yeah.
So maybe but I guess I missed it, but
You mean the?
Yeah, on the first
Yeah, I think I
part.
know what you mean. I think I know which one you mean. You mean
Yeah.
this one? This
Yeah.
one? Yeah. So there's been a lot of discussion about whether this upturn is real or not, whether it's an artifact of the box size, because up here you're limited by how small a scale you can resolve in an MOD simulation. It's limited by how many particles you have in your box, right? And the average spacing between the particles in your box. So people have studied whether this is real or not, and even from a semi-analytical viewpoint. Okay, so there's a kind of modeling called halo modeling, where you try to describe the large-scale structure according to, you think about the structure formation the power spectrum in terms of the halos and how they're clustering. And so from semi-analytical modeling, you will also get this kind of spoon shape. We call this a spoon because it looks like a spoon. So it looks like something that is real, yeah, and not
Yeah.
because of simulation effects, not box size effects. Yeah.
Know how think the green line is obtained with nonlinear correction with perturbation theory.
Yeah.
Does that mean that we don't
It
know
just-
either
it-
that?
It just means your perturbation theory breaks down, and perturbation theory breaks down when the coupling is too large, right?
Okay.
And
Yeah.
now, so perturbation theory is okay up to about here, as you can see, and there are a lot of people who try to do variations of perturbation theory up to about this point. But beyond your coupling, if you like, it's just order one, and you can't do perturbation theory anymore, and it breaks down. And I don't think that's necessarily a problem with that. It's just we know perturbation theory has a limit.
Okay.
Yeah.
I have a curiosity about the last thing you hinted at about the fact that as anisotropic, we have hints that actually there should be anisotropic stress connected to neutrinos, right?
That's right.
What I'm wondering is, behind the fact that we have anisotropic stress, there are a lot of assumptions, right? So when we don't see that enhancement in the multiples, can we really conclude that that anisotropic stress is due to the neutrino free steam and etc.? Because to me it seems like there is a tower of assumptions.
There is always a tower of assumptions in any
That's
of these
true.
analyses, including the neutrino mass balance. So the same assumptions apply, and so you could redo the analysis and ask, do I have an anisotropic? Is the indication of the presence of anisotropic stress still there if I vary the model? And there are people who have explored this, as I understand. So yeah, so you can test it, just like you can vary the way you do the fit by making your background model more complicated and see if somehow the anisotropic stress is degenerate with some other cosmological parameters, like, I don't know, dark energy or primordial tensors or whatever. You could definitely do that. I don't know, I mean, it hasn't been explored quite as much as, say, neutrino mass balance and the robustness of neutrino mass balance to variations, with respect to variations in the fit. But yeah, one could certainly do that. Yeah.
I have also a question. Regarding the amplitude of matter perturbations and structure formation, what is the impact of massive neutrinos on the sigma 8 parameter, roughly the percentage variation?
So again, the calculation or the fit, you mean?
No, fit with
Fit.
data.
So you mean if I have massive neutrinos, do I shift the other cosmological parameters?
Yes.
To an extent, yes.
Sigma 8, yes.
Yeah, to an extent you do. So there are a number of known degeneracies between the neutrino mass and other cosmological parameters. So for example, you put in a finite neutrino mass, you will definitely change the error bars around the dark matter density. So it makes it a little bit wider. Yes, because there's a degeneracy. So Yeah, that's the main one. So there's also a known degeneracy of the neutrino mass with the dark energy equation of state. So you could potentially also shift things there a little bit. Yeah, you normally at the moment, okay, we don't have a neutrino mass measurement. So essentially what allowing for finite neutrino mass does to your fit is to make the error bars around, say, W or dark energy a little bit larger than it would have been the case if you didn't include a finite neutrino mass as a free parameter. Yeah.
Okay, thank you.
Yeah.
Yeah, I saw this was one of the slides. Can you tell us a bit on the CMB bounds on the neutrino decay?
Oh, CMB
I
bounds.
saw-
Yeah, I was.
We already discussed it. but
I
think
was actually going to talk about that next Friday anyway. I was going through these slides and I realized that, hang on, wasn't I going to talk about that on Thursday, next Thursday? But I'll say something about it. So basically, neutrino decay is the same idea with the isotropization. What makes decay a bit much nastier than looking at just self-interaction is the fact that if you had decay, your decay is beamed. Okay? So if you have relativistic neutrino that's coming in and it decays away in flight, then the product neutrinos are beamed. In other words, the angle that is emitted relative to the initial path of the neutrino is very tiny. It basically goes like the inverse Lorentz vector. And if the particle is massive, this is further suppressed by the mass gap between the two. Okay, so you have an additional phase space gap over here. So what it means is that if you're trying to, and also if you have the inverse decay, which should also happen, these particles that come in to coalesce to give you the heavier neutrino have to have exactly the right momentum. They have to meet at exactly the right angle before this process can happen. So if you're trying to use decay to isotropize, so you want to use decay and inverse decay to turn an initially anisotropic fluid into something that is isotropic, it takes a very, very long time. Okay? So the question is, how long does it take? And in the literature, about 10 years ago, 2005, 2016, there were some people who tried to estimate these guys. And they said that the time scale that it takes essentially goes like the gamma factor of the initial neutrino times the rest frame lifetime of the neutrino multiplied by this inverse of the two small angles. Okay? And what we did with a couple of students was to actually revisit the problem and calculated that from first principles. So you write down your Boltzmann equation and then systematically reduce that to something that's tractable. And what we found is that this dependence on the two small angles is actually the -2. And so what it means is that your isotropization time scale is actually much longer than initially thought by these guys 20 years ago, almost 20 years ago. Okay? And so we visited that, and that led to bounds that were quite different. So these are our bounds, and these are the earlier bounds by these people, and you can see that this goes at 10 to the 9 seconds, whereas we're finding something that is 10 to the 5 seconds, or maybe a few hundred seconds. Okay? And also the dependence on the neutrino mass, the decay neutrino mass, is to the power 5 as opposed to the power 3. So that changes the decay bounds completely, because the isotropization time scale is now totally different. And the difference is that they guessed theirs, we calculated ours. So, yep.
In neutrino decay, there's some particle, BSM particle lighter than neutrino.
Yeah, so here it has to be
within
some BSM scenario. So you have a heavier neutrino decaying into a lighter neutrino, which could be one of the standard model neutrinos or maybe a right-handed state. We didn't ask because it didn't matter for our problem. And you have some boson. That's just quantum statistics. So
Already, like if the lighter particle in thermal bath initially, that
yeah,
already
so
ruled out by NHS.
yeah, so no. So what happens is that these scenarios of decay, they are called recoupling scenarios. So what happens is that you have, so if this is temperature, okay, no, hang on. This is time and temperature goes this way, okay, your weak interaction rate will drop, okay? Gamma weak goes like GF squared T5, right? And then you also have the Hubble expansion rate, which goes like this. So Hubble is T squared, okay? And then Planck mass, okay? So in the standard case with weak interaction, this is neutrino decoupling, okay? Now, let's say I have this decay happening, and if I ask what is the decay rate, then what happens is that the decay rate would go up like this. So this is gamma decay. So what happens is that you have initially neutrinos that are coupled to the bath, then they decouple from the bath, or they are free streaming a little bit, but then when the expansion rate drops below, and when the decay rate goes above the Hubble expansion rate, they are recoupled again. Okay, so you start from no free streaming at early times, free streaming for a little bit, and then they couple together again. And so once you get to this point, and you're looking at something which is essentially nu h going to nu L plus some phi, then all you're doing is to exchange energy between these three particle species within the neutrino sector. So you have three decoupled neutrinos, they could decay, you create a phi, but there's no pre-existing phi in this picture. Now,
I have a nice question, like that 25% dark matter, 5% value.
yeah.
Thing actually coming, considering a lambda CDM and fitting the data,
Try,
considering a lambda CDM and then
yeah,
fitting the data.
that is lambda CDM, yeah.
So let's say I have a hot dark matter, then
Yeah.
this number will change, right?
A little bit, tiny little bit. It does, I mean, that was actually related to your question. So if I put in a neutrino mass as a free parameter in my fit, that shifts your dark matter content by a tiny little bit, if you do the fit that way,
If you consider astrophysical observation like rotation curve and all,
Yeah.
that is consistent with 25 and 4.
I don't think rotation curves really tell you much at that kind of precision level.
So there's no constraint from astrophysics.
Well, if you want to use rotation curves to determine what is the dark matter density, you also need a very good measurement of what's visible. And I don't think our astrophysical observations are at the level where you really see this, 5 times more dark matter than. So I mean, anything that's more scale will be more subject to.
Let's say, in a hot dark matter scenario, is it safe to consider omega to be 0.12 or something?
0.1 omega, small omega,
Yeah.
like this one,
Of the
0.12.
yeah. Of the yeah.
I mean, okay, it's good enough. I mean, it's you will see a bit of a shift. There are always error bars. Okay, there are always error bars around it, and the point is that if I do a lambda CDM only fit, my omega would be, I don't know, 0.12 plus or minus something, I don't know, 0.01 or what. If I add neutrino to that fit, that number probably shifts a little bit in the second decimal place, or maybe third. You get maybe twice as large error bars. Yeah. But as long as I don't have a neutrino mass measurement, if I don't fix the neutrino mass to some value and then do the fit, then they're all more or less consistent. I don't know if I'm not answering you.
Let's say there is no cold dark matter, so only dark matter is a hot one.
So hang on, what do you have? You have what, sorry?
The dark matter is only the hot one.
Yeah.
And neutrino plus another particle that only create a hot dark.
So it's only hot. It's entirely hot. Yeah.
Then this production will
Well, your entire theory will fail anyway, because you will have no objects. Yeah. If you have 0.25 hot dark matter, your theory won't even work.
What about then axions and all?
The
What about the axions, dark matter?
axion dark matter. Well, axion dark matter is cold. So axion dark matter is a totally different game. So axion dark matter, QCD axion dark matter is usually said to be about microelectron volt in mass. But the thing is that they are not produced thermally. They're produced via phase transition. So you should think about it like a condensate, where you only have 0 momentum modes present. So they're all just sitting there very cold, doing these kind of coherent oscillations. Okay? And you have So they are cold, and it's okay for them to have such a small mass and to have a lot of them in number density. But once they scatter, you will have a problem. They will become hot. But the thing about QCD or whatever axion dark matter is that they don't scatter. Yeah, the cross-section, scattering cross-sections are so small that you can essentially ignore any possibility of making a thermal population of these things. Okay, so they're just cold, zero Earth mode, and then it's all good.
So this analysis seems to be strongly depends on the fact that the assumption that neutrino two-body decay, right? Like because like you are dealing with the angles of the neutrino beams. So like, is there any way that you can put the general constraint of the neutrino in body decay?
In what decay?
Like the three-body, like.
So as I was saying, that we basically what differs between what these people did and what we did was that we consider the kinematics more carefully. We did that for 1 to 2. We never did it for 1 to 3. We probably should do it for 1 to 3. I can't really say off the top of my head whether things would change significantly. But this is definitely something that just applies to 1 to 2. Yeah, so I can't tell you what would happen if I do 1 to 3. It will probably, it may change things a bit. Yeah. But then you will also have more coupling constants to worry about. It will be a high order effect. So it's possible that they'll be different. But I don't know, I can't say. Maybe I should do it. Now that you reminded me, now that you're telling me, maybe I should do it just for the fun of it. I'll give it to a student to do.
Usually it's the teacher who gives homework and not the student the teacher, but okay.
Yeah, but the thing is that it's... yeah.
I have another question, sorry.
Yeah.
Focusing on the plot of the matter power spectrum, it seems the presence of the massive neutrinos suppress more the power spectrum in the nonlinear regime on small scales. May you comment about these weird recent results about the compatibility with negative massive neutrinos in the parameter space to suppress less the power spectrum? And also, what do you think about the possibilities to explain the nonlinear regime to the scalar regime in the effective field theories of large-scale structure, about also the BAO peak reconstruction?
Okay. So what was it? So you're talking about this plot, essentially.
No, also the previous one with different massive. Yes, also this one. Oh, yes, this.
So remember your first question again.
Yes, it seems that the presence of these massive neutrinos affect the power spectrum on small scale. What about the possibility of negative?
Negative. So if you naively put in a negative neutrino mass into your equation of motion, it just makes no sense.
Yes, I agree. But with
my understanding, okay, so are you probably referring to that paper by Nathaniel Craig and these people when they talked about negative neutrino mass, right? My understanding, and I have to admit I did not read the paper very well, they were basically just parameterizing. They just say that, okay, if I have positive neutrino mass, it corresponds to suppression. The negative neutrino mass would correspond to an enhancement.
Yes.
So I think that's all they were doing. So from the modeling point of view, I think that was that. And they were just trying to use that to indicate that maybe there's some other physics going on that we are not modeling, that we are not taking into account. Okay? So the model itself is just made up. Now, from the point of view of the data, well, I mean, I guess there's something I also noticed. It's that if you look at the one-dimensional posterior from like the DESI data for the neutrino mass, it doesn't peak at anything. It peaks at 0. So if you keep continuing it, it looks like it's going to peak in a negative mass region. So that's basically what these guys are trying what they were trying to do. You know, they were trying to say that maybe the data is telling us that there are more perturbations than the lambda CDM case, even the lambda CDM case. For me, I think that's indicative, probably indicative of some unknown, unaccounted for systematics, which could be in the data, it could be in the modeling of the signal. I don't really know. I don't have anything to do with that data. But for me, it seems like there's still something they don't understand. You can interpret that as new physics. I would be hesitant to do that, but I'm conservative when it comes to inventing new physics scenarios. Yeah, so that's my first comment. The second comment is EFT of LSS, right?
Yes.
I think the thing about EFT of LSS is that they try to explain this region, right? But my understanding of EFT of LSS is that they always have to supply some input data from small scales that are determined by M-body simulations. So ultimately what it means is that you're still relying on M-body simulations to basically provide an anchor, if you know what I mean. I mean, it's perhaps a little bit more sophisticated than what people do with fitting functions. People used to do fitting functions. They motivated fitting functions in some way from maybe semi-analytical modeling. Then they try to determine some parameters from simulations, and then they use that to to predict any nonlinear corrections for different cosmologies. As far as I'm concerned, I think EFT of LSS falls into the same category. They are just making it slightly more sophisticated sounding. But I don't know, maybe it's a very negative statement. But that's just my opinion of it. So in the end, if I have to, the bottom line is that if I have to rely on an M-body simulation to supply an input, then for me, then I would just say you may as well just do the M-body simulation. Yeah, so that's what I think.
Thank you. Yes, maybe we can postpone other questions for the break, and let us thank again. Yes.
Yeah.